Our first speaker is Colin O'Halloran, and he works at Kinetic in the UK, and he's going to talk about verifying control software.
Thank you.
All right.
So, thank you, John. Why am I talking about industrial control software of all places in Google? Why is it relevant? Well, control software appears everywhere. In the car that you drive, your central heating system is a very simple controller. Aerospace, and it's aerospace I'm going to principally be talking about, in particular flight control. I should say this is work I'm presenting jointly with my colleagues Karen Stevenson and Phil Clayton, who can't be here today, but it's the combination of work that's of a lot of people that's gone on in Kinetic. So, clause verification. Well, clause stands for control laws in Z. Z being a mathematical specification language. What's clause verification about? Well, put simply, at the moment, it's a form of code walkthrough, but with tool support to generate what we call a witness script. Now, the witness script is basically a record of how you've stepped through the diagram and related it to the code, hence the code walkthrough. But the witness script then itself becomes an input into another tool, which generates a refinement conjecture. So it's like faking formal refinement with existing code and existing specification. So that's why I say it's a conjecture. This is where you're saying the code, we conjecture the code refines this specification. Now the task is to actually prove that the refinement is correct. I'll talk a little bit more about that. So the proofs that will come out of the refinement conjecture, which will be input into our tool set, are for free. That's largely automated. And hence, the purpose of this is to find discrepancy between specification and code. Now, the specification itself might be incorrect, and we have examples of that where we're looking at third-party software. So it's not always that the code is wrong. Sometimes, bizarrely, the code can be right and the specification is wrong, especially when you get into industrial development processes, which are multi-nation. And as I say, we provide formal verification, but we've largely concentrated on deskilling this activity so that it can be done by recent graduates, or indeed undergraduates, where we've used sandwich students who take between a year between their academic courses, worked at Kinetic, and have used this. And another important aspect is it's not about just the first time you develop the code from a specification. It's also about when you make changes, iterations to the specification, and hence to the code as well. You can largely reuse a lot of the work that has been done before. And that's very important in this area because control laws are often subject to iteration. So because it's about controlling a physical process, it's not until you get behind the wheel of the car, try it out, and you feel, well, actually, that doesn't feel quite right, the handling of the car, and you start tweaking the control law, or indeed, in terms of an aircraft, how it handles. So the clause method. It verifies code that's implementing a Simulink specification. So Simulink is kind of a de facto standard in this area of control systems, and it's a product of the Mathworks. And the analysis of the specification and the code is done by procedure, and then line by line. And the essence of the kind of walkthrough part, the witnessing activity, is really relating specification signals to code variables. So it's a very simple activity. You have a diagram, like block diagram, with wires between the blocks. Those have names, and you just say, well, what name does this correspond to in terms of a variable in the code? So it doesn't get much more simpler than that. Now, the reason why you might think, well, can't that be done automatically? The reason why we have this manual facility to do that is because we look at not just code that's been generated automatically, but also code that's been produced by people. And people have a lot of variability. And so you need to be able to take that flexibility into account. And that's why there's a human element to this when people have produced the code. So it's very flexible. As I say, the tool support that we have supports comparison and does checks for correctness. Now, of course, it doesn't do everything, so we have to make some constraints. One thing is, and a very important simplification, is that it compares a single model iteration of the Simulink with a single code iteration. Now, a control system is basically a loop which continues forever. So you're looking at the code that's inside that loop, and you're comparing it with a single iteration of the model. You don't lose any generality by doing that, but it's quite an important aspect from the point of view of loops we largely don't have to deal with. We do have to a certain extent, but it simplifies the task quite considerably. We can optionally check initialization. And currently, we're looking at a subset of Ada called Spark. I say not loops, plus a little bit more. But if you think of the Spark subset of Ada, for those of you familiar with that, that is essentially the code language that we deal with. We also have to subset the Simulink language as well, because Simulink is, as the name implies, it's really based upon simulation. And you can transform your simulation for a continuous real-time control system down to the point where it's discrete. It's not until you get to that discrete representation that you can actually use automatic code generation. So again, it's natural sort of restriction to make when you're looking at verifying code against the Simulink. Simulink diagrams, as I say, describe dynamical systems. They have block diagrams which define a function, f. So the function, the input to the function varies over time, as does the output. But we abstract time away. So we're looking at logical correctness. And continuous sampling is the means of providing the input into the control system. So in a simulation-based part of Simulink, it uses numerical methods to give approximations, good approximations. You go to a discrete version where you're actually going to actually implement this on an embedded system in a car or in an aircraft. It may have to be a restricted version of this numerical approximation for efficiency's sake, especially when you have hard real-time systems. But if you sample the inputs sufficiently often, you get a good enough approximation, good enough to control an aircraft, even an unstable aircraft. So I'm going to launch in now. I haven't talked very much about the technical details about clause. That's the second part of my talk, if we have time. I'll talk about the evidence that we generated from an experiment that was done back in 2001. So this work came from assessment of third-party software for Eurofighter. Now, the requirement for the control system, the flight control system for Eurofighter, is expressed in Fortran. And that's a kind of, because of the how long it's taken to develop the aircraft, it's a legacy situation. So in the late 80s, the experimental data and model was expressed in Fortran, and that was the starting point, and it continued to be the thing which is maintained as the specification. And from that Fortran, you then develop, let's say, code in this subset of Ada called Spark, which is then implemented on distributed system. So the requirement is about simulation and getting the requirement right for the control system. The implementation has to deal with real-time aspects, the demands, and because of the processors that were used at that time, it couldn't be done on a single processor, so it had to distribute it over several processors. Now, as part of the development process, of course, you that point, you do a unit test, and you find maybe some coding errors, and you do an iteration, and you continue around that. Now, as part of our third-party assessment, so we're producing additional evidence from point of view of safety certification, the requirement that was in Fortran was translated into Simulink. So that has an advantage in itself in the sense that the Simulink is a nice paradigm for control engineers to actually understand what the control system is doing. The trouble with Fortran, of course, is it mixes software engineering issues with simulation issues. So you're kind of moving these, getting rid of the software engineering issues about efficiency of the running of the Fortran and so forth, and expressing it directly into the kind of nomenclature which a control engineer would be familiar with, like gains, integrators, delays, and so forth. Now, part of our work is about confirming equivalence between the manual code and this Simulink representation. Now, most of the discrepancies that we found were to do with the incorrect translation of the Fortran into the Simulink, unsurprisingly. That's a informal or at best semi-formal process. So when we found a discrepancy, it was most often in the Simulink. It had not correctly captured what was in the Fortran originally, whereas the code had, because that was carefully developed. But we got to the point where the Simulink was more and more faithful to the Fortran representation until we started actually finding occasional errors in the code. Now, I say occasional, it's like one potential issue for every 10,000 lines of code. That's extremely good software development, but it was extremely expensive to do as well. This is for an aircraft where it's unstable, and any sort of error in the code potentially could lead to loss of the aircraft. So it needed to be done very carefully. It's a very highly dependable piece of software. However, we did find occasional issues. So now in 2003, we have this kind of baseline Simulink representation. And we used the automatic code generation facilities that are available from the Mathworks to generate ADA code in a Spark subset, and then performed the same unit tests after we had used our techniques to verify the automatically generated code. And essentially, we got 100% unit test pass. Now, what that means is that, in principle, the software that we had generated automatically and verified, so there were mistakes in the automatic code generation that took place. It wasn't perfect. It was pretty good. We were able to correct the automatic code generator in order to eliminate those errors. By passing the unit tests, it's kind of the first hurdle in order to get flight clearance. So that's an important hurdle. Now, I emphasize this because what we're trying to do is not show that in this experiment that the software is perfect. What we're trying to show is it's as good as the criteria used for the manually developed code. So as well as doing this work, we took measurements of the activities that we were going through, and we also had access, an independent party from us outside of Kinetic had access to the data in terms of development, the manual development process. So we're able to do a comparison against the use of clause and the automatic code generation facility for the commercial automatic code generator, to be able to compare the time and hence the cost of using the traditional, conventional sort of careful development process for the flight control system, as well as clause. And as you can see, there's quite a saving to be made. I think. Sorry, I can't.
Is the y-axis is person hours? Or?
Yes, that's right. Yes. So total person hours. So the question was, is the y-axis to do with the number of hours that people take to develop code And that's correct. Now, we did a repeated experiment, but also we've extended the technique somewhat to state flow, which is a kind of sister notation to Simulink for state-based descriptions. And again, the verification techniques we use for state flow is less mature, and so it costs, and in terms of time and money, a bit more than clause, but it still stands good comparison. So the point here is that looking at the use of formal verification, formal methods, not from the point of view of getting perfect software and that making claims that the software is so much better than conventionally developed software. In a sense, that's meaningless in a quantitative way because you can't possibly measure the fault density or the failure rate for software that has such criticality. There's a certain level, about 10 to the minus 3, 10 to the minus 4 failures per hour, beyond which you can't measure meaningfully, especially which you're talking about before the deployment of the aircraft or the car or whatever. But you can meaningfully compare the cost of using the methods to pass the same criteria, the same bar, as it were. So that's what we have done and what we've concentrated on. And so the message trying to get across here is that the use of formal methods and formal verification, actually you can create a business case for why it can displace traditional methods, conventional methods, certainly in the high dependability area. So, looking a bit more detail, breaking it down. So for new code, for current, this is averages over a number of projects, and is anonymized industrial data. Includes co-production from Simulink and the verification. For new code, it's 100 man-hours. For amended code, it's 54 man-hours, with a typical productivity rate of 20 lines of code per person per day, at a maximum. Now, if you're using clause and a static analysis tool, Malport, which looks at runtime exceptions, and again, comparing it like for like, for new code, rather than 100 man-hours, it's 20 man-hours. For amended code, and remember, for control systems, you're always iterating and changing the code, it's less than 1 man-hour as opposed to 54 man-hours. And that's where you get real huge savings. That's where the killer is in terms of costs of development of control systems, especially for high dependability ones. And so the typical productivity rate is 40 to 100 lines of code per person per day. But I say it's for the amended code, which is the real essence of the compelling reason to use these sort of techniques. So I'm going to give some figures about the sort of scale of verification and the what we found. Now, this is rather old data. We have recently done a flight control system again, a new version of it. But this is from February 2007. So it started in November 2006, February 2007. So it's not much in terms of elapsed time. The control system was implemented by 353 scheduled subprograms, procedures, and that includes subprograms called within the subprogram itself, so procedures called in procedures, within the scheduled overall system. And that consists of roughly nearly best part of 34,000 lines of non-blank, non-comment ADA codes. So it's real code that does stuff. And we found suspected compliance errors in 10 subprograms. We're not labeling them definitely as errors because remember, the specification, even in the Fortran, can get out of step with the implementation occasionally. And that's an important issue to find. 305 of those subprograms or procedures were completely verified by machine proof. Okay, so there was no human judgment. It was sentenced completely formally by a machine. A further 11 did require some human assistance because, again, we're talking about manually developed code with human variability. So there were some aspects of using code style or maybe efficient algorithms because of the hard real-time aspect of it, which we hadn't come across before. So those further 11, also assuming certain preconditions being established by previous procedures, which were scheduled before the procedure that we were verifying. Now that left a further 14 that contain residual verification conditions that were discharged by a person. So we had good confidence in correctness. And when I say verification condition, this is something which is huge and has been hugely simplified down to the point where a human can actually make a look at it and make an informal formal argument, if you like, pen and paper sort of argument for why. And remember, this is a commercial activity we're doing, we haven't got endless resources or time. We've got to do it to a time and a budget, hence why we made some compromises. 20 subprograms had residual verification conditions that were not provable, and that's due to insufficient information to prove correct. So that might be because the information wasn't present in the Simulink diagram, but it is an actual assumption that you can make about the system. So we had significant confidence they were correct. And 4 subprograms didn't have suitable specification to verify against. It was just, again, another part of Kinetic are doing this translation from the Fortran. And again, they're doing it to a tight budget and time constraints. And they just ran out of time or ran out of money in order to correct the Simulink that they had produced for us. So they would produce some Simulink, we'd try to verify it, find that there was a discrepancy, be able to point out, well, actually, the Simulink isn't correct in this respect. They go back, find that discrepancy, correct it. But at some point, because it's a time-limited, budget-limited project, they would just give up on that particular point. And that's the reality of what's happened there with those 4 subprograms. So of the just over 20,000 verification conditions analysed, 19,617 fully machine-checked proofs. So that represents 98% of the verification conditions mechanically verified by a theorem prover. And the verification cost is a fraction of a conventional verification. So we get a high degree of confidence, much greater than you would through conventional development and verification, but at a fraction of the cost. And that overturns the kind of prejudice they had for formal verification that you only use it for critical system safety or security critical because it costs so much. It's gold plating. Well, I think what we can see is that if you bound it, scope it, and you automate, which you should be able to do with formal verification, then actually you can reduce the cost tremendously and it becomes an industrially usable technique. And I say the real benefit is during requirements evolution, because you reduce the time and the costs. So the adoption argument for these techniques is based on cost, not reliability. Now, I would maintain that you're going to get much better software out of this if you use these sort of techniques, but you can't scientifically, quantitatively show that for this highly dependable software. What you can show, though, as I say, is how much cheaper it is, how much quicker it is. And when you're talking about control systems where you can be iterating time and time and time again, and time to market in the automotive industry is the key issue, then actually that's a powerful business argument for the adoption of formal verification techniques. Now, I've talked about it in terms of control systems, but I don't see any reason why the principles can't apply in different sort of areas. It's about identifying a problem domain, using the constraints of that problem domain, and perhaps making further constraints. But these sort of constraints are adoption of a programmer's conventions about the sort of constructs that they use, or the modeling language. These are the things that you typically do anyway in an industrial setting. So it's not onerous constraints that you can impose. They're the sort of constraints that you would do anyway for industrial benefit. So using that sort of thing, I think this sort of principle can be used elsewhere to drive down costs, increase automation, increase confidence in terms of the software, and then the case for using formal verification becomes compelling because of the cost reasons. Now, current work is concerned with, rather than human-generated code, is automatic code generation from Simulink. Now, this is gaining in popularity. The Mathworks themselves are selling more and more autocoders. And there's kind of been a wave of enthusiasm and adoption for automatic code generation from models anyway. Applied Dynamics International have a code generator from Simulink to Spark, the subset I was talking about of Ada. And I say we've been talking to ADI in business terms, so saying, well, actually, we don't want to modify your code generation. We want to be able to check it. Now, the code generator they have, all it has to do is to give us hints and clues about how it's gone about generating the code automatically. So it's doing the work, it's just putting in little comments about how it's gone about doing it, what decisions it's made. And from that should be enough in order to generate a witness script. And from the witness script, we can generate a refinement conjecture. And from a refinement conjecture, we can automatically generate verification conditions and then check the correctness of the code that's been automatically generated. So they don't think there's a lot of, we're not paying them to do this. They're doing this because it's not a large amount of effort and the potential return. Now, we're still in a process of doing that, but we hope to resolve, bottom out the sort of issues that we're discussing with them in the next few weeks. It's the determinism of the code generation that's been done automatically and the automation of the witness script generation that makes automated verification possible. So, in principle, you should be able to press one button to generate the code from the model that you have, press another button to actually automatically verify that code, assuming that there aren't any errors. And that's because we've shown that it can be done largely with a very difficult situation where you have human beings varying the way they generate code, so in a sense, non-deterministically generating code. When it's done deterministically, you can cover all possibilities, or you can at least learn where you come across cases where so you haven't done it before and increase the automation. But in principle, I can't see any reason why you can't do it completely automatically. And therefore, you get potentially huge cost and time savings. The sort of savings I put up before, which represented sort of 60% savings, well, they just get blown out because I say it can potentially be just a press button. So I say we've been able to deskill this formal automated verification facilities to a code walkthrough with tool support and with proof. It's highly deskilled, successfully used by undergraduates, not graduates, and the automation of verification along with independent automated code generation is a potential commercial offering. And I think that's important because if we can show that this works commercially, then again, it's not an academic argument about reliability. It is about a business case for why this should be adopted to displace more costly and potentially less reliable development techniques and V&V techniques. So we haven't got time to go through the second part of my talk, which talks about Simulink and takes you through an example of witnessing and how the verification conditions are generated. Go into a bit more detail. But I can take questions. If you want to talk to me offline, then I'll be delighted to take you through the kind of principles. Were there any questions at this point?
Actually, a question. So you said that one of the main benefits of your approach is being able to make it repeat. It shouldn't be too long, the question.
Okay.
Should I stand up to the mic?
We all want to hear what he's going to say.
Okay, so the question said, you said that one of the main benefits of the approach is that you can reuse your results as the requirement change or as the code changes and so on. So how does that reuse work if you have automatically generated code? Suppose that I have some code, I start from some kind of spec, automatically generate the code, I do some proof which is mostly automatic, but I still need to do a few things manually. Now I make the change in the original code. Now, this the compiler or the translator that generates the actual thing can get something completely different. So how much of reuse is then possible if you do have this translation?
Okay, that's a good question. So I think in practice, you wouldn't reuse for automatically generated code and automatically generated information for a witness script. But in a sense, it doesn't matter because you can just... you're talking about manually changing the code that's been automatically generated, aren't you?
No, manually changing the starting thing from which you generate the code.
Oh, well, in that case, then it's perfectly fine because if you've changed the model, which is what you should do, change the model rather than the code, then you use the automatic code generator, which will automatically generate the witness script for you. So you're not reusing, but you're not losing any time or in terms of, because it's been done automatically.
So, but then is the correctness of the generated code done fully automatically, so there is no manual steps involved? So the manual steps are only at the level of the model. Is that what you're saying?
Yes. When you have an automatic code generator, it's just at the level of the model. What I was talking about previously was when human beings are developing the code, and then because there needs to be human intervention because of that, that's where you can take advantage of the just modifying part of the code means you just have to modify part of the witness script. And that's been our experience. But when you're using automatic code generation, this is why it's so great to use it, it just generates everything automatically anyway. Sorry, Andrew was...
Hi, so this is maybe slightly out of scope, but in terms of cost, so one of the costs, if you move between applications, and that's what you want to do in the future, there'll be a maintenance cost in terms of your proof infrastructure.
Yes.
The infrastructure that supports automatic proof.
Yes.
Could you say something about that?
Yes. So a great interest of mine is not just about the automated verification now, it's about the expertise you would need to maintain if the code generator changed, and that would require new proof strategies or tactics to be done. Now, again, you can still see how commercial business can be made out of that, because if you have sufficient number of automated verification tools out there, you sell enough licenses, it'll maintain the core expertise in order to be able to do that. What I'd really like to do is be able to use the sort of techniques that have come from AI to be able to do proof planning and proof maintenance. So you often don't see that the code changes that radically in terms of especially if you're using an automatic code generator, that will evolve. It won't make a big change. You get different versions and it'll gradually change. Now, what you would like to do is to have a proof planning facility, and there's work in Edinburgh, for example, on that sort of thing, which I would like to adopt, to be able to kind of track those changes and adapt the proof, or the proof tactics and proof strategies as the code base evolves, so the proof strategies evolve as well. So I see that would be a significant thing to do to drive down the costs even further for the future.
I was wondering about the verification and validation of the automatic code generators. Is that something that you, are the code generators things that you write, or are you buying them from third parties, and how confident are we in those? I guess it would be similar to like a compiler, the amount of time, the extent to which you could be confident of the compiler.
Exactly right. I mean, that's the beauty of it, is that we're not producing any special automatic code generation facility ourselves. We're taking third-party commercial code generators and adding that assurance. So it's like, it doesn't have to be reliable at all, in a sense, because from point of view of dependability, it'll just, you use these techniques, add it in, and it'll say, well, the code doesn't match the model. This automatic code generator is rubbish. So you wouldn't use it for commercial reasons because, you'd never actually get to market. Of course, in practice, companies who sell code generators like this, like the Mathworks, of course, do a certain amount of validation. Certainly sufficient that it works most of the time. But in their business models, of course, they can't afford to spend all that money for specially certified code generators. And the beauty of this is it doesn't cost them anything except for recording the sort of steps that they're taking in terms of doing code generation, which they're doing anyway, just recording it, making that available externally, and then being able to use that information to use a facility like this. Does that answer your question? Yeah. Okay.
I have a little additional question to that. If the code generator would have been proven correct, is it then necessary to go through the entire procedure as well you applied, or would it be sufficient that the code generator is correct?
In principle, if you've proven the code generator correct, then you wouldn't need this technique. But again, the beauty of this is that if you can produce the information and at very little cost to do that, then why not use this as well? It doesn't cost you anything. It should be just click of the button. Now, my problem with proving code generators correct is that if you want to change it, then there's a lot of effort and cost involved in doing that. And that we've seen that sort of thing in the past with compilers, so that it's been shown that it can be done, but then the language changes because it evolves every 10 years. Now, in the commercial world of simulation models and so forth, they can change every 6 months. And so that means that you either have to lock it into a particular version of the modeling language and code generation and the automatic code generator. But you're right, technically that is a viable thing. From a commercial point of view, it's more difficult. Okay, thank you very much.